Hello, statistics friends. Let's take a look at some inferential statistics with the Central Limit Theorem. And I'm going to start off with some data that you all provided, screen time. So this is what you all estimated for me, your average daily screen time. And let's see, we have 75, so these are my statistics students for 2026. And you can see the distribution here up to 11 hours per day is a relatively normal bell-shaped curve, but then we have this skew to the right, indicating there might be outliers. And if we take a look at the 95% rule here, we can see that the below two standard deviations from the mean, so the mean here is 6.38, so in this column right here, two standard deviations to the left is negative, so that means there are no people in this group that have an unusually low screen time compared to the rest. However, the upper cutoff from the two standard deviation rule or 95% rule is around 13, so we can see we have several people here. It looks like probably 4 people who have an unusually high amount of screen time compared to the rest. And the box plot based on the IQR rule shows there are, again, a couple of people. So those two upper values here, these two stacks, those 2 points, indicate the 2 people who have an unusually high amount of screen time compared to the rest based on both rules. All right, so again, take a look at that distribution, and let's jump into StatKey to take a look at this data. Copy it, and what we're going to do is a confidence interval for what we think the population mean screen time per day is in hours. All right, so StatKey, and we are going to do a confidence interval for a mean. And then we will edit their data out and paste ours in and double check. We have a header, but we don't have a first column identifying each of these values. So we have the right button selected. That is important. And here I can see there's 75 with a mean of 6.379. We will rarely explore the median. Maybe if you take a future statistics class, you look at confidence intervals or hypothesis tests for median. We're focusing on averages and proportions. Standard deviation should be 3.348. See if that matches my spreadsheet. Yep, looks good. Same mean, standard deviation, too many decimal places there. Let's tone that down a bit. Usually you go 1 more decimal place than the data. Data here has 2 places, so let's bump that up to. Okay, so that's the usual rounding rule, 1 more decimal place than the data. Okay, so once we have our data plugged in there, we're going to resample on this using our sample generator here. And so again, what we've created is 1,000 new samples, and every time I point to one of these dots, the bootstrap sample changes here, which is not, each of these individual bootstrap samples is not important. They're resamples from the original. But it gives us an idea of what other variation there might be in the population if this is a good representative sample that I started with. So I'm going to assume that's a good representative sample of community college students. A lot of students take statistics. All right, so that's not enough though. We need more than that, and we were trying to generate enough so the standard error starts to stabilize. And usually 5,000 to 6,000, it starts to stabilize. Okay, I'm going to stop there with 6,000 resamples. All right, now notice this right here is a very symmetric bell-shaped curve compared to the original, which was sort of symmetric in this part, but definitely skewed right. And there's a thing in statistics called the Central Limit Theorem, which says if you take a bunch of sample means, so here I have 6,000 means, so I'm only plotting from each of these resamples the average of the sample, right? So I'm kind of condensing that information, compressing it, and this is going to give me an idea of what other averages might be like for similar samples from the population of college students, community college students around 2026. And I can generate a confidence interval by jumping to 2 tails, and the default is a 95% confidence interval. but we could decide to do a different one, like a 90% confidence interval, 0.9. So a 90% confidence interval will be a little narrower. Sometimes we even do things like a 99% confidence interval, in which case I will get a wider interval. What is this interval down here at the bottom? 5.41 to 7.388. That's what I expect the population mean for community college student screen time per day. So I think then, let's copy this and write about it. So this is again a review from a couple of weeks ago, but it's relevant to what we're doing this week. Other things to notice, the mean for my sample, let's grab that too, is going to be usually a little bit different than the mean in the distribution, because again, we're looking at variations on that original one. Into the notebook. Okay, so based on this sample, if I think it's a good representative sample, I think that the average screen time of community college students is about 6.379 hours per week. I'm 95% confident that the population average screen time is somewhere between 5.41 hours and 7.388 hours. So if I round to one decimal place, then I'm saying my 95% confidence interval, let's scribble it up here, is about 5.4 hours up to about 7.4 hours per day. Right? So again, this right here is my 95% confidence interval. And again, my interpretation of that always starts off the same way. We are 95% confident that the average, we've got to be clear to point out this is an average, you can call it a mean if you want. Daily screen time, we have to define what the numbers mean. I'm claiming the population is community college students. Oops, and I realized I just made a mistake because I did a 99% confidence interval. Oops, where's my eraser? In this case, I'm 99% confident is between 5.4 and 7.4 hours. Okay, so hours, I got that it's daily, I got that it's an average, I got that it's screen time, so that's all important information. Yeah, that looks pretty good. All right, next thing I want to do is are there other estimates out there in the world of what average screen time is? So I did a little search and found this website here that claims in 2024 the average amount of screen time was 6 hours 40 minutes for US adults. And again, that's daily screen time, and that's down from 7 hours 3 minutes per day of screen time in 2023. And you can see it's fluctuated a little bit over time, but not too much. All right, so 6 hours 40 minutes. Let's check that as a decimal. So that would be 6. And 40 out of 60 would be 2/3, so that should be 0.666, but let's just double check. 40 out of 60, yeah, 6.67 hours is what they're claiming. So let's copy that, put it in my notes. All right, so we have a claim from this website. Oops, it didn't copy. All right, so claim average screen time for US adults, and most of my students are US adults, in 2024 was about 6.67 hours per day. All right, my sample again, back a page here, was a little lower than that. So I might say, well, you know, I think community college students have a little less screen time than the average adult. All right, so I'm making another claim based on my data and what I found online. So I have another claim now. Community college students watch less than 6.67 hours per day. All right, so I can turn these into hypotheses. So I'm going to say my null hypothesis, that would be the age 0, is a mean, mu. What is mu? Mu would be average screen time for US adults in hours per day. And we're claiming up there that, according to that article, it's 6.67 hours per day. And now I have an alternative hypothesis, call it HA, sometimes H1, and that's going to be mu, population mean. What is mu? Mu is the average screen time for US adults in hours per day, and I think it's less than 6.67. I'm going to go for the usual significance level. Alpha is 5%. And I want to test this hypothesis. So then I have to jump over to StatKey's hypothesis test page. Now, just something to note here, the confidence interval gives me a clue about how the hypothesis test might run, since 6.4 hours is in this interval. Okay, so since it's in the interval, well, I would say community college students really actually watch about the same, even though this mean is a little bit lower. Is it significantly lower? I'm leaning toward no. How do we measure something significantly different? We have to do a hypothesis test. So let's jump this in a new tab. And we're going to do a test for single mean. All right, and then we have to edit the data. So let's cut theirs out. And I need to recopy mine here. And again, I don't want to copy the whole column. I just want to copy down to the last data value. And paste that in. All right, so I have a title, header row, but no first column identifying whose number is what. All right, so there's my same sample size, 75. Always double check you got the right data in there. Have to change the null hypothesis. 6.67 is what we claim the population mean is. And then once I have my data and I set the null hypothesis, then I can start generating samples. And I want to get at least 6,000. I'm looking for that standard error to stabilize. So the standard error predicted by StatKey here is 3.84, and the confidence interval is 3.83. They're about the same. All right, so I'm going to make a note of all of that. Back to the notes page here. According to StatKey, we have a standard error, SE, of about, I'm going to go with the second one, 0.384 hours per day. Now that's not the standard deviation of the, of the sample. That's the standard deviation of the distribution of means, which is also called the sampling distribution. So let's double check that. So notice the spread here is about 0.4, so from the middle, If I go 0.4 to the right, I end up here. If I go 0.4 to the right, I end up around over here by the 7.5-ish. If I look at the original data, it has a much wider spread. Standard error there is 3. Okay, very different. Notice that the standard deviation of the original data is about 10 times bigger than the standard deviation of the sampling distributions we've done here. What's the difference between this sampling distribution and this one? This one is centered at about the sample mean, and this one is centered at the population mean. That's the difference between a sampling distribution for confidence interval versus a hypothesis test. In this case, I want to do what? Left tail, right tail, two tail? According to the less than is to the left, I want to do a left tail test. So to continue my hypothesis test, I have to select left tail. STAT key is always going to put 2.5% in each tail, or one tail if you select one test. You have to adjust by plugging in your sample statistic. In this case, it's the mean, 6.379. So I'm going to adjust this lower value, 6.379, to match my sample, and I can see I'm getting a p-value of about 22%. So I'm going to sketch that out. So let's just make a little sketch down here. I can fit it there. So we draw our best normal distribution. In the middle, we mark the null hypothesis. Mu is 6.67. And then over to the right here, I'm going to mark my sample value. So that would be my x bar, which is 6.379. And that gives me this region here. That's my p-value. And I'm getting a p-value of about 22%, so 0.222 according to STAT key. If I run STAT key again, it might be a little bit different. My sample size is 75, which is not too big, but big enough. Usually if we're going to apply what we're going to do next, the central limit theorem, we want a sample size of at least 30. And again, what is the central limit theorem? Well, the central limit theorem says that if you have a reasonably large sample, 30 or bigger, and you do repeated sampling of that same size, so if I did thousands and thousands of samples of college students of 75 each, and I plot all the averages from each of those samples, I should get a normal distribution, which I can see here. That's a very bell-shaped curve. So I'm just going to check a couple things out. So I'm going to reload STAT key, and I'm going to go to the normal distribution calculator down here. And the normal distribution calculator can work in two different ways. You can give it a z-score, which means you're using a mean of 0 and a standard deviation of 1. I'll come back to that. Or you can enter your data from the sampling distribution, which would be the mean of the sample and the standard deviation of the sampling distribution. So that would be this little 0.384 value. And my sample mean is the 6.379. My population mean is the 6.67. So here's how I use a standard normal distribution calculator. I'm going to edit these parameters and set the population mean 6.67. And again, this stuff is new stuff here is covered in chapter 5. The other stuff I did is review of chapters 3 and 4. And then the standard error of that sampling distribution was the 0.384. And then I want to do a left tail test here, and I want to enter in my sample mean. So that would be the 6.379. So you got to keep these values straight. And the theoretical calculator gives me a p-value of 0.224. The randomization test gave me a p-value of 0.222. So about 22.2%, 22.4%, they're similar. Either way, I reject the null hypothesis here because my p-value is big. So what that means is there is a 22% chance of finding another group of 75 college students with an average screen time of 6.379 hours per day or less. Or less. Okay? 22% chance. That's not uncommon, which means my sample mean is close enough to the population mean to say, they're really not that different. It's not significant. So do I have any evidence that college students, community college students have less screen time than the average US adult? The answer is no, I do not. The evidence here suggests that the average community college student watches about the same amount of screen time as the average US adult. So let's note all of that. So again, this theoretical distribution calculator here just gives me another way to make calculations about confidence intervals and hypothesis tests besides the randomization test. And we're going to compare these two for the rest of the term. All right, what did we just accomplish here? So we do not have enough evidence to support that claim, so let's make a note of that. So our decision is we are failing to reject the null hypothesis. Fail to reject null hypothesis. Our conclusion, so the decision is always about the null hypothesis, the conclusion is always about the alternative. Can you support it or not? So conclusion, I do not have sufficient evidence to support the alternative. So I state that, explaining what the alternative is. So it's important when you do these hypothesis tests and confidence intervals that you write down on paper in words or type it up, what are your claims, what is your parameter? All right, conclusion. We do not have sufficient evidence of what? Well, state the alternative. The alternative was community college students have significantly, oops, wrong order, less screen time than the average US adult. Let's see, I'm missing some things here. Average US adult, that's okay. I need to note somewhere how to measure screen time. Do not have sufficient evidence that, it's an A, community college students have significantly less screen time per day. Usually takes me a couple of drafts to get this with all the right information than the average US adult, right? So I need to, how am I measuring screen time? In hours per day, so I need to make sure that's in there. I need to note that I'm talking about an average. Yeah, and might be slightly better if I take the word average and put it up here. But that's not too bad. I think I got all the right information. All right, so we can't support the alternative, right? It's close enough. It's pretty similar to the average US adult. I'm going to double check this one more way. I'm going to calculate a z-score. So this is called a standardized test statistic. And for now, it's going to be a z-score. We'll learn about t-scores next week. So a z-score for a standardized test statistic for a mean is always the sample mean minus the population mean divided by the standard error. Okay, so again, that's sample mean, x bar, minus the population parameter, which happens to be a mean, so the null hypothesis value. So let's call that null value, which is population mean and then we divide that by the standard error. So it's a modification of the z-scores we learned about back in chapter 2. So in this case, I have my 6.379 minus 6.67, that's what I used, divided by the standard error, 0.384, and then we need to whip that out on a calculator. So I'm going to grab my Desmos calculator. We can just use the Google calculator. All right, so in this case, I need parentheses, 6.379 minus 6.67, and I should double check I got those values right. Close parentheses, divide by 2. No, shit, not 2. Divide by 0.379. All right, double check here. 6.379 is the sample mean. Population, we're using 6.67, and the standard error is 0.384. Oops. Looks good. Negative 0.7578, sure. 4 decimal places is good, 7578. And again, just do that calculation in one shot. Don't subtract, then divide in 2 steps. You have a modern calculator, use it wisely. Negative 0.7578. 7578. Okay, thinking about what that means, for a normal distribution, z-scores have a center of 0, no deviation from the mean, and then if we go out 1, 2 standard deviations to the right, and 1, 2 standard deviations to the left, we expect to find about 95% of the data. Remember that? 2 standard deviation rule. In this case, we have a z-score of negative 0.75-ish, so that would be around here. Let's call it 0.76. And our belief is that this p-value here is about 0.22 something. Remember we looked at that on a calculator? Now, I didn't do it with z-scores. I did it with the population mean and the standard error. So let's go back to stat key and confirm that. So I'm going to duplicate this tab here. And here I'm using mean of 0, standard deviation of 1, which means I have to enter a z-score for the left tail. And down here I plug in my z-score. Negative 0.7578. And I should see I'm going to get the same p-value I did from this distribution. I'm just rescaling. So this distribution has a center of 6.67 and a standard deviation of 0.384. P-value with the sample mean of 6.379 is 22.4%. Right? So again, that's very similar to the randomization distribution. And you're going to have an assignment later this week where you're going to do this 3 different ways. Randomization, theoretical with the null hypothesis value and the standard error, and then you're going to do a z-score, mean 0, standard deviation of 1, plug in your z-score, confirm the p-value, and notice that all 3 p-values are pretty damn close to each other, if not identical. So again, further evidence that I should fail to reject the null hypothesis, that we don't have enough evidence to support the alternative hypothesis that college students watch less screen time than the average US adult per day in hours. All right, so we reviewed here chapter 3, confidence intervals, chapter 4, hypothesis tests, and now I'm giving you a preview of what's in chapter 5 in the 2 sections. And that's about using standard error and a theoretical normal distribution. Take care, do good math. I will see you in the near future.